Time is 9 a.m., so let's get started here. So project number 1 is due tomorrow at noon. Please email it to me by noon. And also remember there's only one project that needs to be handed in per group. Just, of course, remember to have all of the group members' names on the project. And I would prefer if you, for the file name of the file that you send me, please put all group members' names in that file name. And the reason why I say that is because otherwise I get, 15 different projects handed in, all with the same file name of Project 1. And when I put them into a folder in my computer, it obviously makes it difficult to save them all by that same name. So I would prefer if you use your actual names then as the file name that you send me. Test number 2 is 2 weeks from today. Are there any questions? Okay, we were talking about factor analysis. This is the factor analysis model. This model has some similarities to a regression model, but there are also some differences. Let's go through what this factor analysis model represents once again. So what we basically say is this: our data represented by our x's, x1 through xp, so variable 1 through variable p, comes about through this model. That's what we're saying, how this data arrives to us, is actually through this model here that we have represented. And if we look at x1 itself, we see that x1 is equal to its mean plus, then we have a linear combination of some lambdas with some f's. Okay. These f's are called common factors. The reason why they're called common factors is that they are common to each of the x's. So we can see, for example, that f1 is in the equation for all the x's. These lambdas then give us information about how much of an effect that f has on x. Just like how the betas in a regular old regression model, as shown up here, tell you how much of an effect that x has on the response variable y. So if lambda is equal to 0, that says, for example, that an f does not have any effect on x. If a lambda is greater than 1, greater than 0 says it has a positive effect, less than 0, negative effect. These lambdas are parameters that we will want to estimate. The f's are random variables. They have a mean of 0 and a variance of 1. Also, these f's are independent of each other. What I'm telling you right now are model assumptions, essentially. Now, these f's are common factors. Basically, factor analysis is most interested in these f's. Basically, you can have, as I have represented here, up to m different common factors. And our goal is hopefully to find just a need for just a few common factors. Similar to how in principal component analysis, our goal was to hopefully find just a need for a few principal components. So essentially, let's say if m was equal to 2, that says we have 2 common factors. And what this is saying, too, is that our data can be represented in 2 dimensions, essentially, even though we might measure p different original variables represented by these x's. Okay, so the goal is hopefully to find some set of common factors that explain a lot of the information that's in your original data. And hopefully it's just a few common factors that are needed to do that. Now, just like in a regular regression model, where we have this epsilon here that kind of captures all the other information that is needed in order to get y that x doesn't provide you already. Well, in a factor analysis model, we have these etas that kind of play the role of the epsilon in a regression model. These etas are called specific factors, specific because you have a different factor for each of the x's. These etas are random variables. They have a mean of 0 and a variance of psi sub I, let's say for eta sub I. Okay, let's see here. So that's what our factor analysis model looks like. You know, it's kind of a different looking model, but it does have some similarities to a regular old regression model. So each of these psi's that I mentioned, the variance for the eta, it's called a specific variance because it's for a specific factor. Let's see here. Okay, I guess I kind of already mentioned this, and that is that ideally we would like the common factors to account for as much information about the original variables as possible. That is a goal. Now there was, a number of these assumptions that I was mentioning to you. First of all, for example, these f's and these etas have a mean of 0, and that assumption is not really a big deal because if they didn't have a mean of 0, we could basically suck up this non-zero mean into our mu's in our factor analysis model. Also, it's not a big deal that the f's have a variance of 1. We can always change the lambdas if we needed to get it into a new factor that had a variance of 1. An assumption, though, that the model doesn't make that, unfortunately, we can't really check or deal with, is that that these f's and these etas are independent of one another. There's not a good way to check this. One reason is, and I failed to mention this while I was just originally going over this model here, that these f's and these etas are unobservable random variables. You'll never be able to go out and actually observe them, which is different from what we have with a regression model, where our independent variables, well, you go out and you observe your independent variables. You observe your dependent variable. Here, we can't observe these f's or these etas. Similar to, I guess, in a regression model, the epsilons, your error terms, those aren't observable either. Okay. Now, although I have presented this model in terms of the x's, and everything can be done in a factor analysis setting in terms of the x's, typically instead some changes are made to the model. It doesn't affect necessarily your analysis, but some changes are made. Often you will see a factor analysis model in some textbooks represented like this, where now instead of having an x on the left-hand side, now we have an x tilde, and this x tilde is just a notation, convenient notation to say it's the mean adjusted x's. So take an x, subtract off its mean, and you get an x tilde. And often you'll see, again, factor analysis models represented in this manner. It's not a big deal. It's just a different way to represent the model. Also, you will see the model represented in terms of using matrices instead. Notice how this is a little more compact representation of our model that we had previously. So x tilde is a p/1 vector. All my lambdas are put into a capital lambda matrix. This is often referred to as a factor loading matrix. My f's, I could have, let's say, m of those. It's going to be a m/1 vector, my f there. And then eta is going to be a p/1 vector of my specific factors. So it's just a little bit more condensed form of our model. Also, in terms of matrices, then, what does this mean? Well, the f here, remember, all these f's are independent of one another. They have mean of 0, variance of 1. Well, what that says is that you can say is that f is distributed 0i, meaning mean vector of 0 now, and a covariance matrix of I, identity matrix. Okay. Also, eta, distributed mean of 0, covariance matrix of, let's call it psi, where psi is a diagonal matrix with psi 1, psi 2 down to psi p on the diagonal. Remember, all the psi's are independent of one. All the etas are independent of one another. That's why you have zeros on the off diagonal. And here's our actual factor loading matrix. All I did was I put all those lambdas that we had seen previously into one matrix structure. So, for example, this first row corresponds to the lambdas for x1. The second row corresponds to the lambdas for x2, and the last row for xp. Okay. Any questions? So, now also we will typically be working with instead, well, we could work with the x tilde, we could just work with x itself. Typically what you will see in factor analysis is that you're just working with standardized variables for the similar reasons to what we saw with principal component analysis. Okay? So, typically we will be having z on the left-hand side versus x or x tilde. You know, why did I present x and x tilde first? Well, just to show you that you could, but typically, you're not going to have, let's say, variables that are measured in the same units. And even if you do, maybe you have some variables that have a lot larger variances than others, and you don't want that to factor into your analysis. And so typically you work with the standardized variables. And in fact, the R function that we will see that does all of our calculations, or a lot of our calculations for us, automatically standardizes the data. And you can't actually use it without standardized data. A similar thing happens with SAS for the corresponding procedure or proc that does it. Okay, so then, this is what our factor analysis model looks like. Matrix form with now a vector z on the left-hand side. Now, one important thing to remember then with this kind of a model, or when you're working with standardized data, that the covariance matrix for z is equal to the correlation matrix for the x's, which equivalently also would be, let's say, the correlation matrix for the z's as well. So if you wanted, I won't introduce no new notation for that, but that's going to be important. Because remember, what's on the diagonal of a correlation matrix? Well, the variances for the z's in this case, which would be 1. Okay? That's going to play a role in some of the stuff that we're going to be seeing shortly. Also, something, please don't get confused about this. Notice I'm still using the same lambdas and the same f's in this equation as I was before when I had an x on the left-hand side. Now, obviously, if you were to estimate, and you'll see how to do this shortly, if you were to estimate the model with x's on the left-hand side or z's on the left-hand side, would you expect the same lambdas and f's? No. Okay. It's a convenient, in terms of notation, that I don't introduce new notation, say, okay, now I'm working with the z's versus I'm using the x's. So, and this is typically what you see done in most books, is that they'll use the same notation. Okay, let's see here. Now, in order to understand some of the stuff that we're going to be doing next, it would be very helpful if you had a mathematical statistics class. So hurry up, go take one. If you haven't taken one already. Obviously, that's not possible. So I'm going to give you a brief introduction to some stuff that we will be using shortly. Okay. So, suppose we have a matrix A of some constants, just some numbers, and we have a random vector, y. Let's say that you want to know, well, what's the covariance, not just y, but how about A times y? So notice what will be done here is essentially this A, when you multiply by y, allows you to find linear combinations of your y's. So for example, if I had A as, let's say, 1, 1, 0, 1, and I take it times y1 and y2, we see that I will have y1 plus y2 over y2 as the resulting vector. So this A allows you to find particular linear combinations of your random variables. Well, there's a nice little shortcut then if you want to find the covariance of A times y. And that is, you can simply take this A, bring it out in front, and also put it in the back, but transpose it. And so this covariance of A times y is A times the covariance of y times A transpose. Okay, don't worry about a proof of that. Again, that will be handled in like a mathematical statistics class, or also like a Stat 970 linear models class. But just to give you a little bit of background here, where this result comes from is that, and you might have seen this in a Stat 801 course, at least I introduced it in my Stat 801 course. Where this result comes from is the following. Let's say if you want to find the variance of a constant a times a random variable y plus a constant b times a random variable y2, what ends up happening is that you get a squared times the variance of y1 plus b squared times the variance of y2 times, or plus 2 times ab times the covariance of y1, y2. If you want to know more about that, take a look at a mathematical statistics book, such as the one that we use for Stat 882 and 883 here. Okay. Now the second result that we need in order to do the stuff that we want to do here is it's a rather simple one, and that is, let's say if you want to find the covariance of a random vector x plus a random vector y. What ends up happening is that you can distribute this covariance through the plus there and get covariance of x plus the covariance of y. Hopefully that makes some intuitive sense. If what is in x doesn't affect what happens in y, then you can take the individual covariances to find the covariance of the sum. And in case I didn't say this, let's assume x and y are independent. If they're independent, you can do that. Okay. So, why is this important? Well, it's important for this reason here. Let's take a look at our covariance matrix, and we're going to do it for x tilde. Notice a little change there. It actually is also true for just x itself. In the notes I have just x there. It's true for that, but I guess since I already had introduced the x tilde notation, why don't we go with it? Let's say I want to find what the covariance of x tilde is in terms of this model that we have presented, this factor analysis model. Well, let's say that's step 1. Let's put in, for step 2, let's actually put in the model. So it's lambda times f plus eta. Now remember, the f's are independent from the etas. That's an assumption of our model. So using the result that we had up there, we can distribute the covariance through the sum. Now then in step 3 here, using the result that we also had from all the way up here, we can, these lambdas are parameters that we will want to estimate. Parameters are constants. When we pull those lambdas out of that covariance, so that we have lambda times the covariance of f plus, can't talk today, lambda times the covariance of f times lambda prime. Now what's the covariance matrix of f? Well, remember, we have a mean of 0, variance of 1. The f's are all independent of one another. So what's the covariance matrix of f? I, the identity matrix. The covariance matrix for eta, well, remember we called it psi, a diagonal matrix that has psi 1 through psi p on the diagonal. And, of course, lambda times I is just lambda. And so this is what we're left with. Okay. So, why is this important? What's the meaning of this? Well, what this is saying is this. If we have this model structure, then our covariance matrix induced by this model structure is lambda times lambda prime plus this matrix psi. That's what it says. And this is actually extremely important for factor analysis, because when we go about trying to estimate quantities, we're going to use this structure here to help us estimate the lambdas, to estimate the size. That's what we're going to be using. This has a specific name, this structure for our covariance matrix. They're called the factor analysis equations. I didn't invent those names. It's just the standard terms that are used. These are called the factor analysis equations. What we had seen previously was the factor analysis model. Okay. So let's take a closer look at what this looks like then. And what I did was I actually tried to write everything out. So here's my covariance matrix on the left side. So sigma 1, 1 is the variance for x1. Sigma 2, 2 is the variance for x2, and so on. Sigma 1, 2 is the covariance for x1 and x2. Here's my lambda matrix written out, and then lambda prime, and here's my psi matrix. Okay. Now let's multiply out lambda times lambda prime. So remember how to multiply matrices. I'm going to take this first row, let me make my pen a little bit thick, and normally I would then take it times the first column of the matrix right next to it. But remember, I'm taking the transpose of that matrix, so what ends up happening is I'm taking the first row of lambda times the first row of lambda prime. Well, notice I have lambda 1, 1 times lambda 1, 1 plus lambda 1, 2 times lambda 1, 2. And so in other words, I have the square of the lambdas in the first row. Okay, let's do the resulting 1, 2 entry then of this matrix multiplication. I'm going to take the first row of lambda times the first row of lambda prime. And I get the sum of these lambdas multiplied by each other. Okay. Next, let's actually do the addition here. Well, it's fairly simple because notice how I have all these zeros on the right-hand side here. And so only the diagonal elements change when I do the addition. And so this is, let's say, a non-matrix view of what, well, I guess you're still looking at matrices, but you're looking at the inside elements of the matrices. This is what this covariance matrix looks like. So what this means then for us is this. For example, the variance of x1, based upon our model, we're saying it looks like this. Take the sum over all your common factors of the corresponding lambdas for that x. And then plus, then the specific variance, I can't write, plus the specific variance for that corresponding specific factor. Also, notice what this means too. The covariance of x1 and x2 is equal to, I'll just draw a circle around it, the sum of these lambdas multiplied by each other. So notice the specific variances do not play a role at all. Only the factor loading matrix does. These lambdas.
So the equation here should be covariance xi and xj, right? So we have 2xj here.
Excuse me?
It's covariance matrix have 2xj. You have covariance xj with xj. Should be xi and xj. Right?
I'm sorry, I'm not following what you mean. I mean, this is my covariance matrix. Okay? So this is the variance of x1. This is the covariance of x1 and x2. And since the matrix is symmetric, of course, then that's also the covariance of x1 and x2.
In below syntax, you have a covariance xj with xj prime.
Yes. And what's your point?
So should it be covariance xi and xj rather than covariance xj with xj?
No. This is just some dummy indices to represent that they're different. You know, perhaps I should have said j not equal to j prime. Okay? I mean, you can put i's in there too. It doesn't matter. It's just a way to say in a general manner that I have two different x's. Sorry if that wasn't clear. Any other questions? Okay, So some more terminology then. And again, don't blame me for all this terminology, although I am presenting it to you. This is the terminology that's typically used in factor analysis, and so that when you get out of this class, you want to read a paper that talks about factor analysis, or even do factor analysis yourself, you know the terminology that's typically used. Okay, so how should I put this? This is actually on page 10. Why don't I just go there? So the proportion of variance for xj that's explained by the common factors is then the sum of these lambda squared divided by the variance of x sub, in this case, x sub j. So in particular, if we look at the variance of x1 here, let me get a highlighter out, the proportion of variance that's explained by these common factors then is this sum of the lambda squared divided by sigma 1, 1. Okay? This numerator in this proportion is called the communality. So this right here is called the communality. Why? Because remember, these common factors are common to each of the variables. And people have said, okay, let's just call this the communality as a way to denote it. Ideally, we will like this proportion to be as large as possible. Because notice what that says, that if this proportion is large, then that says then that the psi part of this variance is small. So meaning that your specific variances are small. Well, let's relate this now to a regression setting. So here's our regression model, once again, that you've all seen before. Now, essentially, the epsilon there kind of plays a role of this eta, this specific variance. And also this epsilon here, typically we say has a variance we call sigma squared. Well, notice that the smaller that the sigma squared is, essentially, the less that these epsilons are varying. And what that means also in terms of a regression model, the more information that the x's are explaining about the y's. So, now again, relating this to then the factor analysis model, we want these psi's to be as small as possible. Because that's like having sigma squared, as small as possible in our regression model. Saying now our common factors are explaining a whole lot of information about our x's. And that would be a good short answer question on the test. Okay. So again, as I had written before, this is what our variance looks like in terms of our model. It's a communality plus a specific variance. Now here's another term that people often use. These specific variances are often referred to as the uniqueness. Well, why? Well, because again, we have these specific factors that are specific to each of the x's, and they have a specific variance associated with them, so they are unique in some way. And so people like to use the word uniqueness to describe them. Again, I'm introducing this terminology to you because you might see this again later. In particular, in R, you will actually see something in our output referred to as uniqueness. Okay. So, now remember that these lambdas play a very important role for us. Just like how the betas play a very important role in your regression model. You use the betas, their values, to help interpret the effect that X has on the response. In factor analysis, we use these lambdas to help interpret the effect that F has on X. And so what's interesting then is that if you were to look at the covariance for X of J and F of K, you get their corresponding lambda, essentially. So let me actually do a split screen here so we can see the model again. all the way up here. Do some erasing. So, what this equation is saying is this. If I want to know what's the covariance between x1 and f1, both are random variables, that covariance is lambda 1, 1. So that, again, describes how these two random variables are related to one another. So again, if lambda 1, 1 is 0, then that says that, f has no effect on x. Linear effect. If lambda 1, 1 is greater than 0, it says it has a positive effect. Now, this is actually represented by the covariance that you see there. I'll let you look at the proof on your own. It does require some mathematical statistics to do it. Okay. Now, what if instead of working with x's, or x tildes even, what happens if I work with the z's? What happens to our factor analysis equations? Well, now instead of having a sigma out in front, you can instead put a p there, your correlation matrix. And again, the diagonal of the correlation matrix is always 1. What's on the diagonal is always 1s. So what that means then is that the variance for each of the z's would of course be 1. And so then the sum of the lambda squared plus the corresponding psi is equal to 1. Always. So then what's the proportion of the variance that then these common factors then explain about the z's? Well, just simply the sum of the lambda squared. Also, let me make this little change here. If I look at the correlation between z sub j and f of k, let me blow that up so you can see a little better. I don't think I had used this notation before to represent correlation. Some books use different notation. I have correlation of z sub j and f sub k, or equivalently what we had learned in the data distributions and correlation section. I had instead used this notation. This correlation then between z sub j and f sub k is lambda sub jk. Why is it that? Well, it just comes from using that result up there. But also notice what this means then for us, too, is that these lambdas now have a particular numerical range to them, because the correlations are between -1 and +1. So it means then these lambdas in our factor loading matrix have to be between -1 and +1. Okay. We will get to a numerical example soon. Just going to take a little bit. Let's talk about now solving the factor analysis equations. What that means is that we want to use this relationship that we had just found to come up with parameter estimates, to come up with the lambdas, come up with the psi's, for example. Now, unfortunately, this is not as easy as we would like. Here's why. Okay, so let's work with the correlation matrix here. Suppose the correlation matrix is known. That means that there are p times p plus 1 divided by 2 different known quantities. Why? Well, let's take a look at the case where p is equal to 2. So here's my correlation matrix. P, 2 times 2 plus 1, p plus 1, divided by 2 is 3. So there are 3 known quantities. Here's 1, here's 2, and here's 3. So with a correlation matrix, there are p times p plus 1 divided by 2 known quantities, essentially, without duplicates. And for lambda itself, there are p times m different lambdas that you need to estimate. Why? Remember? Well, let's go back to our equation just to make sure you see this. Just split screen one more time. So how many? So notice I have p different equations there, and then I have m different common factors. Each of them has a specific lambda, so p times m is the number of lambdas that I have. Also, in our psi matrix, remember it's a diagonal matrix, there are p different unknowns, these corresponding variances. So in the end, the number of unknowns that we have that we would like to find estimates for are m times p plus p. Or in other words, p times the quantity m plus 1. Now, back in your old algebra days, you learn that when you have a bunch of unknowns, you find a corresponding set of equations and you solve the system of equations. So what we can do is, with the stuff that we do know, set up p times p plus 1 divided by 2 equations. But the problem is, the number of unknowns is not going to match up, typically. And so that in the end, what we might end up actually having, again, remember back to your old algebra days, more than one solution may exist. Well, that's a problem. Which solution do you choose? Let's take a look at an example that further emphasizes the problems that can occur with a factor analysis model. Now, this is an example where the number of unknowns that we have matches up with the number of knowns that we have. And this will always happen when you have one common factor. So let's say that I have p equal 3 and m equal 1. We have 6 equations, 6 unknowns. So if you take p times p plus 1 divided by 2, you get 6, for example. And so what we're saying with our factor analysis equations is this. I have this correlation structure, and I'm going to set it equal to what our model says our correlation structure is. So that means, for example, 1 is equal to lambda 1 squared plus psi 1. And you can write out 6 equations based upon what you see in your factor analysis equation. You could do a little bit of algebra and show that lambda 1 squared is equal to rho 1 2 times rho 1 3 times, or divided by rho 2 3. You can go through some algebra to do that. Now here's where some problems can still occur. Take this out. Suppose I have this as my correlation matrix. This seems like a reasonable correlation matrix that one can have. So if I set this here as equal, oh, come on, computer, work for me. Then I have 0.3 times a negative 0.3 all over 0.3. Can that happen? I don't know how you can take a square of a number and get a negative number in the end. So this is another problem then that occurs with factor analysis. Is that you can have particular situations like this that cannot exist. Here's another example. Suppose this was my correlation matrix, and this is obviously still a possible correlation matrix that one could have. set this equal to then what your model shows as your correlation matrix. And using this equation that we saw here, you can show that lambda 1 squared is equal to 1.44. Okay. But remember, for let's say the variance of Z1, that's 1, set that equal to 1.44 plus a psi 1. Psi 1 is a variance. Can that variance ever be negative? It's been a while since I've taught a morning class like this. Perhaps it was a long weekend. I've counted at least 4 people who are falling asleep in this class. I remember once when I was in grad school, I had a morning class, or early morning class. It was I think it was 8 or 8:30 a.m. Linear Models 1 and Linear Models 2. It was a theory course for stat majors for your second year of your master's program, and I had a horrible time trying to stay awake in that class. And so, what I tried to do was I always would bring a snack. Often it was peanut M&Ms. So I bring some peanut M&Ms with me to class, and once I start feeling tired, I get those M&Ms out, and I start, eating a few. But I was just so tired that in the process from getting the peanut M&M out of the bag and into my mouth, I would kind of start falling asleep, and I would drop it. It was kind of a classroom like this where it was kind of elevated, and so the M&M then would roll all the way down to where the teacher was. Fortunately, the teacher it was actually Dallas Johnson who was the teacher, the author of one of the recommended books. Fortunately, he never figured out it was me who was doing that. But in the end, since I was falling asleep in that class, I would have to work extra hard then after class to understand the stuff that I missed during class because I was falling asleep. So as a little warning to you, and from someone who has been a grad student once before, by falling asleep in this class, in the end you'll be working harder after class to try to make up what you have missed. Too bad though Dallas Johnson didn't record his lectures. That would have helped me too. Anyway, the main thing of mentioning all this stuff here is that estimating these models is not necessarily a simple thing. You can have multiple solutions. You can have cases where there are no solutions at all. To some respect, you might think, well, is it really worth the trouble of having this, this kind of a setup here for your model? And I will have to admit to you, I'm not necessarily convinced it is worth it. But factor analysis is a commonly used tool. Some people find this very useful. And again, to be honest with you, I don't typically use factor analysis myself. Doesn't mean it's not important, though. I'm just giving you some of my biases, and you can make a decision if you want to take my biases in. Okay. So finally, how do we estimate one of these models? So you can notice on page 16 where we are actually going to get to our example here. But we do need to talk a little bit more about how we estimate these models before we get to the actual implementation. Typically, the way that factor analysis models are estimated now is through just one method. There are other methods out there, but typically it's just one method now, and that is through maximum likelihood estimation. I would expect many of you have seen maximum likelihood estimation before. But if you only come in here with a Stat 801 background, you may have not seen maximum likelihood estimation before. So I feel as though that we do need to talk a little bit about what is maximum likelihood estimation. And so that's what these additional notes that you should have been able to get from my website. Let me just verify that indeed that I did put it out there. I hope so. Yes, this MLE supplement. We're going to start going over this little MLE supplement, which gives you a brief introduction to what maximum likelihood estimation is. Brief enough so that you have a general idea of how it's done so that we can apply it to a factor analysis model. Maximum likelihood estimation is a topic that would be talked about in detail in a mathematical statistics class. For those of you who have had me for Stat 875, you essentially have seen this introduction before, so sorry, but I don't really see a reason why to change the introduction because I thought it worked then, and so I hope it works now. Okay, so we're going to talk about a very, very simple case where maximum likelihood estimation is used. And this is to estimate, let's say, the probability success parameter for a Bernoulli distribution. All of you should have seen a Bernoulli distribution before. And let's put it into an example context. Suppose we talk about how to estimate the probability success for a field goal in football. And so let's let y denote if a field goal is successful or if it's a failure. We're going to let y be equal to 1 if it's a success, y equals 0 if it's a failure. In that kind of setting, then, our probability distribution, then, is a Bernoulli. That looks just like this. Again, this should look familiar to you. Pi is the probability of success. Also, to put this into context, suppose that we're interested in just 40-yard field goals. And so what we do is maybe we'll go out to Memorial Stadium and we take a sample size n. So just imagine talent bowl cleaning. I want to take a sample size of n of field goals in Memorial Stadium. Do you mind if I go out there with your place kicker? And so I'm going to take in our case, in our class, we've been typically calling this capital N. I end up using lowercase n there. I don't think that's going to be too confusing. And so suppose we go out and take a random sample of field goal results. Maybe 10 field goals, for example. And so y1 would be then the result of the first field goal. 0 for failure, 1 for success. Y2 is the result of the second field goal that's attempted, and so on. And using this data, this information that we have gathered, we like to come up with an estimate for what the probability of success would be at a distance of 40 yards. And the way that this is often done is through using what's called a likelihood function. What this likelihood function measures is what are plausible values of pi, our probability success parameter. What are plausible values? This is how the likelihood function is formed. First of all, notation. L is our function for likelihood. It's a function of pi, our parameter. And notice we have this little vertical line here. How is that vertical line usually used in statistics? What does that usually mean? Conditional or given. So L of pi given my observed data. And all that a likelihood function is you just simply take the product of all your Bernoulli distributions, evaluated at either y equals 0 or y equals 1. That's it. So I can make this a little bit more of a condensed form and use a product notation. And I can put in my Bernoulli distribution, do a little simplifications, and this is what I end up getting. Pi raised to the number of successes times 1 minus pi raised to the number of failures. Is everyone comfortable with that? Okay. Well, let's just say that when we did go out to Memorial Stadium and we kicked those field goals, we had 4 successes out of 10 trials. Notice how it doesn't really matter which trial or which kick was successful or not. If you look at the likelihood equation, the only thing that is up there is that sum of the y's. For those of you who've had a mathematical statistics class, relate this to the concept of sufficiency. And so what we can do now is that since this is a function of pi, why don't we just stick in possible values of pi in there? And essentially what the likelihood function does, it will keep on increasing corresponding to the more plausible a particular value of pi is. And the most plausible value of pi is what actually causes this likelihood function to be maximized. So I plug in pi equal 0.2 into simply this equation here, where sum of the y's is equal to 4 and n is equal to 10, and I get 0.000419. Now I plug in pi equal 0.3. Well, notice now my likelihood function has increased. And it keeps on increasing in this case all the way up to pi equal 0.4, And then once you go past pi equal 0.4, it starts going down. So the value of pi that maximizes my likelihood function is 0.4. That is called the maximum likelihood estimate. And that is what we're after with respect to factor analysis models. We want to find what the maximum likelihood estimate is for the lambdas. It's going to be a lot more complicated than what I did here for the simple example, but the concept is the same. And you can take a look at my code on your own, but this is a graph of what the likelihood function looks like. You remember the curve function? I simply use the curve function to actually graph it. And we can see that the maximum does indeed occur when pi equal 0.4. Okay? Essentially then, this likelihood function says the most plausible value of pi is 0.4. Notice how this makes sense in the context of this field goal kicking example. We had 4 successes out of 10 trials. Well, what's the proportion of successes? 0.4. So it makes sense for that to happen. This is just a little bit more mathematical way to basically find that is true. Talking about math, or speaking of math here, one can actually find, instead of just substituting particular values of pi in there, one can actually derive what the maximum likelihood estimate would be for any particular setting here in this particular case. Here's how it's done. First of all, while it's not necessary, it just often makes things easier, find the natural log of the likelihood function. Why? Well, if you take a look at what our likelihood function is here, if you substitute that inside that log, well, then you can start using some properties of logarithms, such as if I take the log of a raised to the b power, I get b times the log of a. Hopefully this sounds familiar to you. Also, if I were to have log of a times b, that would be log of a plus log of b, all the stuff you learn in algebra class, or pre-algebra class. And so you can see with the logarithm here, this stuff that's in the power up here essentially comes out. And also I can now I can add this stuff together as well. So once you find the log, natural log of the likelihood function, take the derivative with respect to pi. Set the derivative equal to 0, solve for pi. That's your maximum likelihood estimate. Step 2 and step 3 applies stuff that you would learn in a Calc 2 and Calc 3 class. Will I ever ask you to do this mathematically like this? No. After all, calculus is not even a prerequisite for this course, sadly. But I can't control that. But this is how it's done. And you can take a look at the details here on your own. And after doing that, I find that pi is equal to sum of the y's over n. That's my maximum likelihood estimate. Since this is an estimate, I want to differentiate that from a parameter. We will typically call this pi hat. Just like what we do typically in statistics, estimates have hats on top of the symbol. Okay. On your own, if you're interested, you can take a look at how to find maximum likelihood estimates for mu and sigma from a normal distribution as well. Now, with that as background, let's go back to page 15 of my regular notes. Now, in this case, we have a lot more complicated likelihood function. This is what the likelihood function looks like. If I can assume that x1 through xn is a random sample from a multivariate normal distribution, notice that this is the first time I've ever actually used a formal distributional assumption in any of the factor analysis stuff that we've done so far. If I can make that assumption then, well, what is then the likelihood function? If I write it first in terms of mu and sigma, it's just the product of n different multivariate normal distributions. That's it. Now, where does the factor analysis model part come in? Well, remember our factor analysis equations. Sigma is equal to lambda, lambda prime plus psi. So I simply substitute in there, wherever you see a sigma, I substitute what our model says. Then instead of having a mu and sigma over here on the left-hand side for what the likelihood function is a function of, I have now lambda and a psi instead. So, to find the maximum likelihood estimates then for these lambdas and these psi's, what do I do? Well, I try to maximize, I find the lambdas, I find the psi's that make this likelihood function as big as possible. It's not, unfortunately, that simple of a process, though. When I was looking at the example with trying to find the maximum likelihood estimate for pi, one could, in general, actually derive it. Instead, since I have a lot more complicated equation, you cannot just analytically derive what the lambdas are, what the psi are. I mean, I cannot just write out one equation. Lambda 1 is equal to some information in my data. Lambda 1 2 is equal to some information in my data. I can't do that. So instead, what I have to do is use numerical iterative methods to help me solve, or I shouldn't say necessarily solve, to help me maximize this likelihood function and find the lambdas and the psi's that do that. Okay. Again, depending upon your background before you came into this course, you might not know what I mean by an iterative numerical method. So let's put it in the context then of our simple example involving the probability of success, that pi parameter. In this case, iterative numerical methods are not necessary, but if one were to do this, one would do something like this. First of all, come up with some initial estimate of what pi should be. Let's call it pi with a superscript 0 on it. And maybe I might say my initial estimate is 0.5. Now, if you're using, without going into all the details, an iterative numerical method, you can come up with a better estimate for pi. Maybe it might be 0.42. Okay? At step 1 of the iterative numerical method process. And then what you do is this. You look to see, are they close to one another? If they're closer to one another, stop. You have found that maximum likelihood estimate. If they're not, keep on reapplying this iterative numerical method. Let's say step 2, I'm at maybe 0.40, we'll say 0.405. And you look, the previous 2 iterations, are they close to one another? If they are, stop. If not, keep on going. I'm going to keep on going here. And this whole process keeps on going and going, until you reach a point where there's very, very little difference in successive iterations. And when that happens, you say that your method has converged. It has converged to the actual estimate that you're looking for. That's how it would be done in that simple situation involving pi. Now imagine this in the more complicated situation involving factor analysis models. That's what's done. Do you think convergence is always guaranteed? No, it's not. In fact, it's not with respect to factor analysis models either. If convergence is not obtained, should you use the estimates that, let's say, a statistical software package spits out to you? No. Because if you keep on going, doing more and more iterations, what will happen is that you're going to get different estimates for your parameters. So it wouldn't make sense to use that. Okay. So I presented the likelihood function in terms of the covariance matrix sigma. Well, you could also do it if you have standardized data. You can also put a p in there as well and make corresponding changes. And then finally, the actual function R that's going to do the magic for us, you could say, is a factor analysis. And they're going to find the maximum likelihood estimates for us, do the numerical iterative methods. Okay. Finally, we get to the data example. So I'd like to do a data example a lot earlier, but the problem is there's just a lot of stuff that we need to know before we can get to it. So that's why it takes us so long. Okay, so we're going to go back to the goblet data set. And we're going to use factor analysis there for it. Our goals are to, discover let's say, the true dimension of our data, just like what we did with principal component analysis. But now we're applying the factor analysis model. And then a second goal is to come up with groupings of our data. We won't be able to do that today, but we will eventually, hopefully next time. So here's my goblet data set. I'm going to make the same little adjustment to each of the variables as we saw before, because that's what the researchers, how they wanted to group their goblets together. They didn't want, let's say they want to group similar shapes. And here's how I use the fact_anal function. The first argument in it is x. And this is where you put in essentially what your variables, your original variables are. W1, W2, W4, W5, and W6. Notice we're using kind of a similar syntax as what we did with the print_comp function. Notice how we have a tilde here as well. The main difference is that we use x as the argument name. How many common factors do you want? Well, what you'll see later is that 2 common factors will work out, generally speaking. And so I'll show you later how that determination is made. Let's just apply it here and say I want 2 factors. My data is in goblet 2. And then I have an additional argument, rotation equal none. Don't worry about that. I will explain that later. I'm going to put the results into an object called mod.fit2. So let's go ahead and come on over here to 10 so I can execute this code. Okay. Now, one of the first things that you should do once you get the results from any kind of function that's new to you is type names mod.fit2. And so inside of mod.fit2, we can see some of the stuff that's available to us. So for example, mod.fit2 $converged, true. What that means is that my parameter estimates did converge. So that's great. I can use this model. Let's do another one. Let's see here. How about correlation? This is actually my regular old estimated correlation matrix using the methods that we discussed in the data distributions and correlation section. We're going to be using that and making some comparisons later. Now, another thing that you should do is determine, well, what is the class of the object that is returned to you from the function? Well, it just so happens to be called fact_anal. And so if I want to see the methods functions that are available to me, I can do methods class equal fact_anal. And notice there's only one methods function that's available to me. If you remember with print_comp and also the LM function in the introduction to R notes, we always had a method function corresponding to summary. We don't see one here. And what does summary do? Well, it would summarize information that's inside of this object return. Instead, all we get is essentially, when I apply this, just essentially a list of the stuff that you get like with names. So there is one methods function that is available to us called print. So if I did print mod.fit2, now we have some information summarizing the fit of the mod. Okay? Before I get into explaining that information there, I want to talk about a little bit about how R works. Now, if I were just to type mod.fit2 itself, this is what I get. Exactly the same thing. Well, why? Well, the way that R works is when you have an object like this, and you just simply do mod.fit2 and then hit enter, R, by default, will go to a print function. It will look for it and print off whatever the print function gives you. And in fact, that's what happened here. So that's why you get exactly the same thing. But one reason why I wanted to talk about this print function is that there are some options with it. Let me make sure I get the argument name right. You remember an argument name called cutoff that we saw with printcom? We would often set that to equal to 0 in order to make sure that all the coefficients for our principal components were printed. Well, we're going to do exactly the same thing here, and that makes sure that all our lambdas are actually printed. Otherwise, by default, any of these lambdas that are less than 0.1 in absolute value will not be printed. So if I go back up to our original output, notice you don't see anything there. Okay, let's talk more specifically about what's given to you in this output. First of all, I was actually just referring to this. We have something called the loadings. These are the lambdas. So let me actually go back here to my output so I can write on it. So here we have lambda 1, 1 hat, lambda 1, 2 hat, and so on. We also have some stuff under the heading uniqueness. Remember that word that we saw earlier. This corresponds to the estimated specific variances. So psi 1 hat is 0.16. Again, we would like these psi hats to be as small as possible. The smaller they are, the more information our common factors are explaining about our original variables. So for example, remember how the variance, the estimated variance in this case of z1, which of course will be 1, that's equal to the sum, the lambda 1k, k equal 1 to 2, hat on top of there, plus the estimated specific variance, 0.16. So we can see then that the estimated communality, the information that these common factors are explaining about the first variable is 0.84, or 84%. So we can see, for example, with the sixth variable, the common factors are only explaining about half of the variation in that particular variable. Also, before I forget, I want to make sure I say this. I know I said it earlier, but fact now will automatically standardize your variables before it's actually run. And there's no way to get around it. Yeah, thank you. So then what is our factor analysis model? This is what's shown on page 19. So I simply took all those lambda hats and I put them into this structure here. A common question for me on a test will be, estimate the model with a certain number of factors and then write out what that estimating model is. This is how you would do it. So that's my estimated model. Now remember the important role that these lambdas play. They allow you to interpret what these common factors are actually representing. So common factor 1, notice how you would just be looking at this first column when you would do the matrix algebra. And notice all these lambdas, lambda hats that is, are not close to 0. Of course, remember they're going to be between -1 and +1, but they're not close to 0. So then common factor 1 then, what's that representing in terms of our original goblet data? instead of scaled by height, total width. Yeah. So kind of like an overall measurement of our goblet, taking into account that we've rescaled the data. Remember how principal component number 1 kind of represented the same thing. Now, sure, there are some parts of F1 that are more closely related to particular Z's, but we see that overall it's kind of overall measurement. Common factor number 2, notice we have positive values here. We have a positive value there. We have a negative value. Notice we have one that's close to 0. Let's see if I can do this. I'll dock it on the left side, and I'll bring up the actual goblet itself. So what we see in this particular case for common factor number 2, what it's representing is essentially the cup of the goblet, and also you could say, well, where the goblet actually is connected to the base. It's that versus then Z6, which represents the height of the base. Essentially, the width of the base isn't playing a role. And we found somewhat similar things when we were doing the principal component analysis too. This is not what will not always happen, but the factor analysis has given us somewhat similar results to the principal component analysis. But let me warn you, though. Well, let me first of all say, notice how when you have one of these right here, one of these lambda hats that are as close to 0, it can make the interpretation a little bit easier because you can essentially ignore it. Remember, this is the correlation between Z4 and F2. And so what would be nice is if we could have, let's say, more of these lambda hats that are close to 0, or maybe even more of them that are close to positive 1 or close to negative 1. And in fact, what you're going to see later is that we'll be able to come up with a different factor analysis model. The same number of common factors, but a different set of lambdas that will allow you to perhaps get a better interpretation. Now, that's both a problem and also, I guess, both a good and bad thing about factor analysis, that we can actually come up with a different set of lambdas for the same common factors. More on that later. Okay, let's see here. So we also have this little table here that gives some information somewhat similar to what you saw with principal component analysis that talks about the amount of variation that's accounted for. And this is the amount of variation that's accounted for by the common factors, amount of the total variation. The factor analysis is not as concerned about explaining as much of the total variation as principal component analysis is. So I typically will not look at this too much and will not necessarily be concerned about it if this number wasn't, let's say, extremely high. I do give some information in my notes on page 20 about where these numbers come from. Please take a look at that on your own. Page 20. So we've already talked about convergence. Very bottom, page 20, please make one small change, and then we'll end it there. On the notes, it says mod.fit1. That should be mod.fit2. And then what we'll do next then on Wednesday is that we'll look at what were essentially residuals. Remember in a regression class, you often look at residuals to have an assessment of how good your model is. You would like your residuals to be as close to 0 as possible. Well, we'll do kind of the equivalent in a factor analysis model of actually comparing two correlation matrices as a way to come up with residuals. So with that, we are out of time. Are there any questions? Okay, that's it for today.